My name's Clay Nunnally. I'm with Major League Baseball. I'm a baseball scientist. So just a little bit of background about me. I come from physics and engineering academically. In my career, I've been fortunate enough to work in spaceborne remote sensing for NASA, and then more recently doing test and measurement of the military standards associated with nuclear EMP. So that's my background, and that's, like all of us here, our experience colors the lens through which we look at baseball. So in the beginning of 2018, I joined the Major League Baseball and Greg Kane's baseball data group. And one of the main things I focus on are the test and measurement of two important things to the league. So here's an outline of my talk, but let's start first with a rhetorical question. And what's weird about baseball? Of all the North American major sports, this is pretty unique. It's the hardest sport to explain to an alien, to an objective observer, and our managers wear uniforms. That's pretty unique. We don't have a clock, at least not today. The other weird thing about baseball is that the field of play is different in every park we play in. And Glenn mentioned park bias in his previous presentation, and I think that's important. We're building a park right now in Arlington where we'll be playing baseball in 2020. In Boston, the Red Sox started playing at Fenway Park in 1912, and their opening day was somewhat overshadowed because the Titanic sank a few days later. So this is a very wide range of ballparks, sizes, shapes. They're different environments by elevation, temperature, and certainly their electromagnetic properties. More questions. How accurate is StatCast? How repeatable is it? How does this vary by park? Why do we care about the answer to these questions? Well, this is foundational data. StatCast, specifically the plate crossing data, is foundational to all the things we service. We push this out to all our apps. We push this out to all our broadcasters. And it's also an ingredient in derivative metrics like pitch movement. It's very important. So it's foundational data for the league. I'm not going to answer these questions right now, but I will say how we go about answering these questions, and that's through ground truth testing. So what I want to do now is just break down our ground truth testing process into some parts that can help us understand it a little better. And this process has been developed chiefly by Jeff Kinsrud and Lloyd Smith at WSU, and we partner strongly with them in this testing function. So when we perform ground truth on a park, we control the environment. We want to make sure we're not confusing things when we take data. So we want to minimize noise sources in the environment. We don't want mowers to be driving. We prefer birds not to be flying in front of our radar. We don't want people watering. We don't want the batting cage. We don't want the hitting mat. We want a clean field so we can measure something very specific. And that very specific thing in this context is plate crossing data. We also use a pitch cannon to recreate the pitch event. We use a pitch cannon instead of a jugs machine because it has less noise. It has less noise from a Doppler standpoint. A jugs machine has counter-rotating tires, and every point on that tire represents a noise flood to the Doppler signal. So you can see that video right there. That's pretty much how it works. The pneumatic pitch cannon is useful in that way that it just accelerates the ball and it doesn't have continuously moving parts. So the second part of our ground truth experiment design is that we need to calibrate the strike zone volume. So to jump to the conclusion, we wind up filming these pitch events, and before we film them, we calibrate the volume by taking reference images of this calibration board. There's nothing super special about this calibration board, but it does have two planes that are not collinear, and the dots are a very specific, well-known size, and the spacing is very well-known. When we video these pitches, we want to make sure the play is exposed and that we have a good reference image. During the test, we'll have fiducial references in the image on the plate, which are these little orbs that you see on the plate in this image. All right, the next part is that we actually film the pitch with some expensive cameras. And these cameras are Bannon Research, but they could just as easily be Edgertronic for half the price. But both of these cameras can ultimately measure position of the ball as it's near the strike zone. We also film these at a very high frame rate, at 2,500 frames per second. And at that frame rate, the ball travels about 0.7 inches in between frames. We also have very low exposure times, 50 microseconds. This is to minimize motion blur, but as you'll see when we actually get to the coordinate extraction part of this, it's not super important, but it is important for other applications of this test. And then we also try to get a high pixel density on the volume in question. So pixels, frame rate, those things cost a lot of money, so we want to be sure and spend those things where they count. So we spend almost all of our pixels right at the zone for this test. So the last part of this is typically done in post-processing. But you'll see in this image here, to the left is the calibration board and some still frames from the videos we take. I show this picture just to give you an idea of how many pixels there are per ball in this video. And this is important because when you're doing coordinate extraction, you can expect to be off by a pixel when you're identifying the boundary of an object. And here in this case, a pixel there's about 100 pixels per ball diameter. So if we're off a pixel, we're off by 100th of the ball diameter. So that's the boring part of this. The interesting part is the video. So this ball right now is going about 98 miles an hour. And this is of interest to me because it's so different than what I experience when I watch it with my own eyes. But the important things to look for in this video are how much it travels in between frames and how crisp it looks, that there's not very much motion blur. To extract the coordinates, to actually identify the plate crossing coordinate, which is at 17 inches from the origin on the front face of the strike zone, we'll identify the frame where the ball is closest to that front face. Then we'll take the 3 frames before it and the 3 frames after it, and we'll use a linear interpolation of all those points. So why do we do that? So we do that so we're not banking on being really lucky and actually imaging a ball when it's at the front face of the zone. We also do that so that each frame coordinate extraction is not the whole ball of wax, it's only 1/7, so it's not gonna wreck your whole measurement. And then we have residuals of this line, which are gonna tell us something about how good of a fit this is and how precise this measurement is. Now, typically we represent the pitch trajectory as a second-order polynomial. And I've exaggerated the distance over which we make this linear assumption, but over a very short distance, about 4 inches, a second-order polynomial looks very much like a line. Okay, so that's kind of what we do. We basically, we film these pitches and try to understand how accurate our tracking system is. In 2018, we performed this test at all parks, some more than once. We do over 100 pitches per park, and there's 7 frames per pitch per camera. That comes out to about 43,000 frames where we extract coordinates. And we review every single frame with a person. And that's thanks to the hard work of the people working in the Washington State Sports Science Lab, Alexis, Brittany, and John. So what did we find out? Well, this gives us pretty characteristic fingerprints of how accurately we can track pitches across the league. So that's important to look at one particular stadium, but it's even more important to look at the continuum of the stadiums across the league. We want to minimize how much our tracking system varies from park to park. So this is how we answer that question. We run tests, and these tests are fairly rigorous. We do these tests when we are qualifying or installing new tracking hardware, but we also have this test as an option to health check a particular tracking installation. So everything up to now I've mentioned has been related to plate crossing data, pitch tracking. That's very important to us as a league, obviously because it's foundational, and we also use that to evaluate our umpires. So it's probably one of the most important single points of data for the league. However, we do have ground truth testing designed to evaluate other things of tracking. So here, these are listed here: hit trajectory, pitch release, and then we have a live ground truth. This picture didn't come through. But so we have a Doppler radar that measures the trajectory of a hit segment after every play. And we represent that with an 8th order polynomial and distribute it as normal. So what we try to test about hit trajectories are things that are difficult or things that are important. Things that are difficult for us to measure are typically Doppler transverse trajectories. So they're trajectories that for which the velocity component is going transverse to the front face of the Doppler radar. Those have a much lower signal to noise ratio than something that's coming with a normal trajectory component. And then, of course, there's a range issue. Our radar installations at every park have a pretty unique ceiling to the hit trajectory. They can't measure baseballs that go 1,000 feet in the air. But that's good because we typically don't have baseballs hit more than 200 feet in the air. So in this video, we are taking our pitch cannon from Washington State and using it to launch a ball. This is over 200 feet. And you can see in the outfield there, that's actually our data quality team that's flagging the landing point of this hit trajectory. So this trajectory is typically difficult to measure because it's very, very high. The things we can sort of resolve from this are at what point the radar ceiling, where it exists, and if the tracking system can reacquire something that it loses track on. So here's an image of the landing points located to within an inch of all over the field. So we did Doppler transverse trajectories, and we also did the really high trajectories, and marked them with flags with our data quality group, and then we measured the location in 3D space with a survey grade Lidar. Won't get into that yet, but that's to say that we know the landing location very accurately, and you can't identify the landing location or predict the landing location unless you have its trajectory fairly well figured out. Another area we do this is pitch release. So I mentioned plate crossing data is an ingredient to a derivative metric, pitch movement. The other part of that is pitch release. Now, right now we report pitch release coordinates in 3D space referenced to home plate as the origin. However, the pitchers use the pitching rubber as their reference for when they pitch. And we try to maintain standards for mounds across the league, but they're probably not all the same. So we run this ground truth test to see how accurately we can resolve the release point with respect to the rubber and also in the coordinate system of the entire park. One thing we aim to do with this is to coordinate or synchronize high-speed video with the Doppler radar signal. Presently, we use a Doppler radar signal to identify a release point, and this is a way to understand what the correlating frames are with that data. And here's our release point picture throwing. This is probably about 120 frames a second. By the way, this is a southpaw out of Macalester College in Minnesota. And here's what it looks like at 2,500 frames a second. This isn't going 100 miles an hour, but it's pretty close. All right, so there's another thing that we like to do here is to understand we can spot check things that are happening in an uncontrolled environment. So previously, all the things I've mentioned are measurements that we can do in a controlled environment, but that doesn't account for all the things happening during an actual Major League game. So this will be the most boring play you guys see this weekend. This is an F9. One interesting note about this game, this is Adrian Beltre's last game. All right, can of corn, nothing important there. But we had our high-speed video cameras filming this game, and we calibrated the volume of the home plate before the game started. And now this is what that play looks like at 2,500 frames a second. So what this allowed us to do is to look at, to do a spot check of plate crossing data in an actual game, and also identify the point of contact on the bat. And this is what we report as the end of the pitch segment, and also the start of the hit segment. And we like to think that those will all be accurate and consistent. So we have these tools and we use them to ensure or understand our data quality. So basically what I would like for you guys to take away from this is that we actually care about data quality, we care about the accuracy, and we are doing pretty rigorous test and measurement to make sure we can resolve park-to-park variation. So yeah, every install we have in every park, we've done this ground truth testing. Extended ground truth testing is what is pitch release, hit trajectory, everything but plate crossing. Those are used as a more global characterization of a tracking scheme, not necessarily just a subset of an install. All right, so there's two subjects here, and I'm going to jump over to the next one. We can have questions on all of them at the end. But I mentioned we use Lidar a little bit in ground truth testing, but we use survey grade Lidar for a lot more. To reset, Lidar is like radar, but it's with a laser. So what Lidar can do is measure some scene, some volume, with very high precision at long ranges. This is typically deployed on drones. It's used to understand Mayan archaeology in Central America, and it's used to look at very minute deflections for rocket launches and construction sites. So there's some applications that we use it for in Major League Baseball that I'll go through now. But these pictures here, you'll see I've got Safeco Field with the roof open. That's kind of the point cloud of Safeco Field. I also have Tampa Bay's their dome, and this is actually the inner surface of Tampa Bay's stadium that it looks like it's the exterior. That's its point cloud. The other image here is the exterior of Oakland Coliseum. And you can see on the left in Oakland's picture, that's where the Warriors play, Oracle Arena. And this has sort of become of interest because this is as-built, 3D data, and we can use that data to understand things like wind and weather around Oakland Coliseum. All right, so those are kind of the end products, the point clouds that we measure and do a coordinate transform and give to our partners and the clubs. Here's an idea of some of the finer detail that you can find in a point cloud. So we have 3D models of basically every park, but they are made before the park was actually built. What Lidar allows us to do is look at what's called an as-built form. So we can not just see what was planned to be built, but how it actually came out. And you can see here, you can look at the mound, very high resolution, the plate, the chalk lines. This is, cool in one sense, but it's also very important for certain things in the game. So earlier in the broadcast, one of the things that we do is predict home run landing distances. And the way we communicate that is we'll measure a hit trajectory and identify where it would hit the ground before it runs into some superstructure. That's the home run distance. And everything works well if the fences are labeled and we track the complete trajectory. Now, those things don't always happen, but at least with Lidar technology, we can accurately measure range to wall in every park. The other thing I should say about Lidar is not only that it's accurate at long ranges, but using the same measurement method at every park ensures a level of consistency. So we generate a point cloud, and you don't even have to know all of the reasons you need a point cloud. Once you have a point cloud, you can do things like this. So, for example, one club we talked to earlier this week wanted to know the exact number to write on a wall because they're installing new panels. This made it pretty easy to do that. All right, another thing that's actually kind of unbelievably in the news recently is the height of the pitching mount and the range of the pitching mount. In the Atlantic League, they're going to experiment by moving the mound back 24 inches at midseason this year. Similarly, in 1968, Major League Baseball lowered the mound by 5 inches after pitchers put up a pretty strong year. So I'm not sure how they measured it, but it does make me wonder what the plus or minus was on the mound height in 1969. So in this image here, you can see not only can I resolve the mound height as reference to the plate, but I can also look at the slope. We actually did this across the league in 2018 to measure mound heights and ranges. And I came away being incredibly impressed with how well our grounds crew controlled the altitude of 6 tons of dirt on their baseball field. So but this is how we can inform decisions in the future about what we do with the mound, because we have accurate league-wide measurements. Maybe some less controversial uses of Lidar technology is camera calibration. So we typically have a live strike zone in our broadcasts, and the Lidar point cloud allows us to map points in the image plane of the center field camera to points in the real world. And what that does is allow us to keep the strike zone in the same place regardless if the camera moves or not. All right, maybe even less interesting is virtual survey. Our parks have tons of cameras, tons of sensors. We have parks that have gigahertz helical antennas in them for reasons I don't yet know. But within a point cloud, you can identify where you want to mount some sensor and what it sees when you point it in some direction. All right, another thing that I use the Lidar technology for is to ground truth our ground truth method. So people ask me, how do I know that the Washington State method is accurate? And it's because we run a tripod ball in a park where we have Lidar capabilities. And this allows us to check how well they can do a stat and a coordinate triangulation, and if there's any coordinate mismatch in the measurement. So it's very revealing of calibration and triangulation issues. The other thing Lidar technology allows us to do is identify location in 3D space of where our calibration panels are. So it's useful. It's a best way to measure where something is in free space. So future applications for Lidar technology in the majors, this is actually automotive grade Lidar. So it's a different subset of the technology, but actually I lied. This is going to be the most boring play you see this weekend. This is a ground out to first base. On the left, it's the video camera. This is at Salt River Field. And on the right, this is measured with automotive grade Lidar. So this can be used for player tracking ground truth to make sure our player tracking is accurate and calibration independent. Some of the takeaways from what we use Lidar for in Major League Baseball: it's accurate at long ranges. It's the best way to measure a park environment. It's calibration independent because the source and the receiver are co-located, and then apart from that, they only depend on the time of flight of the laser pulse. So it's useful to measure park features like the mound, fences. It's also useful for ground truth and useful for accurate tracking. So now, thanks for your attention. I'll go ahead and take some questions from you guys. Go ahead, Alan.
Yeah, in your experiment, the whole plane experiment, I think the first one you talked about, you said that you did a second order polynomial fit. Does that mean you could get the accelerations and then compare those to the tracking and accelerations?
Yeah, so what I should have clarified, for typical pitch trajectories, the whole roughly 60 feet of a pitch trajectory, we use a second order polynomial to characterize that flight path. What we do when we actually videotape it, it's actually, or we record it, it's only about 4 inches of that trajectory near the strike zone. And there, we make a simplifying assumption of using a linear fit. But yes, we can get the incremental acceleration frame to frame and compare that to TrackMan data. That's a good question.
And how does it compare?
Oh, that's a great,
Because that's relevant to.
yeah, that is a good question. And I'm not going to address that in this particular forum. I will say that I do enjoy getting feedback from the SABR community because we know no one thinks about baseball more than you guys. So, I want to get feedback from you guys on, have you thought about doing it this way? Have you ever tried this? What's the result when you try this? So contact me. I'll have a Twitter handle that you guys can use to contact me if you have questions about how we use this technology in baseball. But for now, it's good enough to, you can contact Travis Peterson on Twitter or Ben Jedlovic, and I'll make sure that I get that message. Any other questions? Okay, I'll turn it over to Ben.